Okay, welcome back. And today we're going to discuss continuous probability distributions. So I'm going to spend a little bit of time talking about general probability distributions in the continuous case compared to the discrete case, and then we're going to talk about the uniform distribution as an introduction. Okay. When we talk about the continuous case of a random variable, or excuse me, the discrete case, we can look at probability as area under or area of a bar if we look at a histogram. Okay, so in the discrete case, we can see this, right? So if we just have probability over here as relative frequency, right? And we have this histogram. And let's say we have the values of x. Right? So in the discrete case, it might be something we have, right? And so the bars, the heights of the bars are just the relative frequencies or the probabilities, right? If we look at just the relative frequency definition, right? So if we look at this, in this case, as let's say 0.1, 0.2, 0.3, and 0.4, let's say. And this is going to be the probability of x, okay? Well, if we look at each one of these as one unit difference for each one. So this is 0, this is 1, so there's a difference of 1 unit for each one of these. We could look at the distance or the width of each bar as 1 unit, right? So this would be 1 unit, this would be 1 unit, and so on and so forth. This would be 1 unit. Okay, so we could look at this is the width, the base, right? The base length of each bar. And then the height of the bar is what? The probability. So if we look at the area of each bar, well, what's the area? Well, the base is 1. The height here would be, let's say, 0.25. So if we take the height times the base length, then the area is just multiplying those two numbers together. Well, if the base is always 1, well, it's just going to be 1 times the height. So what's the area? It's just going to be the probability. So we can start looking at area of these rectangles equal to the probability. And so that's in the discrete case. Well, what we're going to do is we're going to treat the continuous case in a similar way. It's just going to be area under the curve instead of the area of the bars. Okay? That's the idea. So in the continuous case, that's exactly what we're going to do. So if we have something that looks like this, that's a nice smooth curve, then we're going to say this here is the function f of x, right? And this here is the value of x on this distribution. Well, what we're going to do is in the continuous case, we're going to treat the area under the curve as probability. In fact, it's equal to probability. So we're going to, obviously this is going to be the height of the bar. This is going to be the PDF, but we're not going to call it the point distribution function or the probability distribution function. In the continuous case, it's called the probability density function. Okay, so in the continuous case, PDF stands for probability density function. Okay. And the CDF is going to be the cumulative density function. Okay. Now here's the difference. In the discrete case, we could calculate the probability that x was equal to some value. Because why? Well, just like I showed you, we could calculate using a formula or the calculator of a particular value of x, because x was discrete. And we could treat also, if you think about as far as synonymous to area of a curve, we're just looking at the area of a rectangle, okay? But in a smooth curve, we don't have rectangles. So if I want the probability of a particular value of x, let's say here, x1, there is no rectangle. It's just a line. Well, a line, think about the area under the curve, right? A line doesn't have an area. It's just a line, okay? It's not a rectangle. It doesn't have a width. So the area under a line is 0, which means in every case, the probability of equal to any value of x is going to be 0. The probability is 0. Okay? So now, what does that mean for us? We're no longer going to be dealing with the PDF function. The PDF function is going to be useless in terms of probability. Okay? In fact, the only thing that you would use the PDF for is if you wanted to draw out the curve. Okay? So the PDF is going to give us the function, okay, f of x, okay, in the continuous case. Okay. Other than that, that's all we're going to use. That's all we're going to be able to use it for. Okay. So whether we're using the calculator or whether we're using tables or formulas, we're going to be using the CDF function, the cumulative density function, for all probability questions. Okay. So that's one consequence of in the continuous case. Okay. The other thing too is the only questions we're going to be able to answer then, and that we're going to be interested in, are questions like this. What's the probability of being less than a particular value? Okay. So in this case here, if we wanted the probability that x is less than x1, let's say, then the area that we would want is this, right? Or we might be interested in the probability of x being greater than x2, right? Let's say that. So in that case, we would be interested in that area, right? Or we might be interested in the probability of being between two values, right? So the probability that x is, that x is less than, excuse me, x2 and is greater than x1. Right? And so in that case, we are going to be interested in this area. Okay? So in the continuous case, we're going to be interested in the ranges of values. Okay? Just like when in the video that we talked about on chapter 1. In chapter 1, we talked about different types of variables, discrete variables and continuous variables. Same idea. Okay? In this case, we're talking about continuous random variables. Okay? So, now the other consequence of being continuous and directly from this result is that it doesn't matter whether we include an equal sign or not for any inequality. So in other words, this probability will always be the same as this probability. This probability greater than will always be equal to the probability of being greater than or equal to. Okay? And then, of course, it doesn't matter where we put the equal sign for this one. It's all going to be the same. So, for example, oops. Okay. So those are going to be the same. Okay. Now, this wasn't true in the discrete case, right? In the discrete case, it did make a difference whether you put the equal sign or not. In the continuous case, it doesn't matter. Why? Because we know it's zero. It doesn't add anything to the probability. Okay? So it doesn't matter whether you include the equals or not. The probabilities will always be the same. Okay? So now, that's the idea of in the general case. Now, let's talk about some of the continuous distributions that we're going to talk about. The first one we're going to talk about in this video is going to be the uniform distribution. That's the simplest one. It's the easiest one to start with. And then you can get the idea of area under the curve. Because in the uniform distribution, like we talked about in other videos, it's a square, or a rectangle, right? It's just a rectangular distribution. So it's easy to calculate probabilities, the average, because it's just a rectangle, okay? So it's just areas of rectangles again, okay? It's just like the discrete case, okay? So let's talk about that in more detail. Let's see. Let's see here. Okay. So as far as a uniform distribution is concerned, a uniform distribution comes up quite a bit, okay? So anytime that the events are equally likely, the outcomes are equally likely, you're going to have a uniform distribution. So what sorts of things have uniform distributions? Well, the time of arrival within a certain period of time of a bus at a bus stop is going to follow a uniform distribution. We're going to talk about smiling times of 8-week-old infants. Those smiling times are going to have a uniform distribution. What else? What other things have uniform distributions? Let's see here. We're going to do some examples, but those are the basic ones that I've worked with and that I've studied. So those are and then there's the examples in here on the smiling times and on the PowerPoints if you haven't seen that. So let's talk about the uniform distribution. So the first thing we're going to do is we're going to introduce all of the formulas. And you're going to see that with the uniform distribution, all of the formulas, except for one, are easily derivable on your own. Okay? All you have to do is remember a rectangle. Okay? So, if we know that x has a uniform distribution, it's going to be denoted with a capital U, and there's only two parameters that completely describes any uniform distribution: the starting point and the ending point. And we call that A and B. So A comma B. Okay? A is when the distribution starts, B is when the distribution ends. So on that interval, the beginning and the end. That's all we need to know. Okay? Now, let's see here. So, if we know this, then here are some of the outcomes. So the probability density function, and here's how I'm going to derive these. So I'm going to create my little diagram here. So I'm going to say that my starting point and my ending point for this distribution is A and B here. So I'm going to draw my rectangle like this. Okay, so there's my distribution. Okay, so now, what do I know about any probability distribution? Especially with continuous random variables, right? The area under the curve, the probability, right, has to add up to what? The probability has to add up to 1, right? And since we're talking about area under the curve, the area under the curve has to add up to 1. So, I know that the area has to add up to 1. Well, what is this? It's a rectangle. Well, we have, how do you find the area of a rectangle, right? We talked about its base times height. Well, this is the base, and this is the height, right? So how do you find the area of a rectangle? Base times height. And what does the area of this rectangle have to be? 1. So now, what is the base here? What is the length from A to B? Assuming that it's in increasing order, right? B is bigger than A, right? This is a number line, right? So what's the distance from A to B? What's that length? Well, it's going to be B minus A, right? So the base is equal to B minus A. Well, if we put in B minus A here, right? And we have this height, and we know that this product has to equal 1. Well, what has to be in here to equal 1? Well, think about it. Think about regular numbers. Well, if I have the area of a rectangle, right? And I know the base is 2, and I know the area has to equal 1, right? So I have 2 times this equals 1. Well, what does the height of the rectangle need to be in order for it to equal 1? Well, 2 times what equals 1? Well, in this case, it's going to be 1 over 2, right? Which, because 2 times a half gives me 2 over 2, which equals 1, right? And so, what if I put in 3? Well, if I put in 3, what has to go here? 3. If I put in 99, what has to go here in order for this to equal 1? Well, it'd have to be 99, right? Because what happens if I multiply across? I get 99 over 99. So that's the key. So if I have this number here, right? This number, right? This is just a number, b minus a. Well, that means I have to have 1 over what? B minus a. And so the height of the rectangle has to be 1 over b minus a. Well, guess what? That means f of x has to equal 1 over b minus a. This is the PDF function, right? The PDF, the probability density function, right? So that's the first thing. So that's what we just found out, right? So we know that the PDF, which is equal to f of x, is always going to be 1 over b minus a. Okay, good. So that's one thing. The second thing is the mean. Well, what's the mean going to be? What's the mean of the distribution for this? Well, it's a rectangle, right? It's a uniform distribution. What did we talk about earlier about, or in chapter 2, about uniform distributions? They're symmetric. Where's the mean of a symmetric distribution? In the middle. Where's the middle of a rectangle? The midpoint of the beginning and end. So smack dab in the middle. What's the middle between A and B? The midpoint. So it's the midpoint of this interval. How do you calculate the midpoint? Well, you take the max plus the min and add them, right? So A and B, so A plus B divided by 2. So it's always going to be A plus B, excuse me, divided by 2. That's the mean. Now, I'm going to give you the next two formulas because you have to derive them, and I'm not going to derive them in this video for this class, since this is just a basic statistics class. But the variance for a uniform distribution is going to be b minus a quantity squared over 12. And then, of course, the standard deviation is just the square root of that. So it's going to be b minus a divided by the square root of 12. Okay? Now, those are the formulas that you need to know for the mean, variance, and standard deviation, and of course the PDF function. Okay? So now, all of this, you won't need all of this, but this will help you as far as with the formula for probability. Because remember, all you have to do for the uniform case, uniform distribution, is remember that all you're calculating is areas of rectangles to find probability. Okay? So now, let's consider our 3 cases, right? So let's put in x1, and let's put in x2, right? So let's just use this as a general case. So now let's say I want the probability of being less than x1. So that's the area I want. Well, let's just think about it, right? Well, if I want the probability that x is less than or equal to, remember it doesn't matter, less than or equal to x1, all I need is to find the base and the height of that rectangle, right? All I need is the area of this rectangle. So what's the base? So it's base times height. Well, what's the base? Well, the base of this is going to be this distance here, right? From A to x1. So the base is what? x1 minus A. So it's going to be x1 minus A times the height. Well, what is the height? We already found out what the height is. It has to be 1 over B minus A. So it's going to be 1 over B minus A. That's the formula for finding the probability of less than or less than or equal to. Okay? So now, what about if I wanted the probability of being greater than x2? So I want this area, right? So I want the area of that rectangle. Well, how do I find the area of that rectangle? Do the exact same thing. So the probability of x being greater than x2, right? So this is going to be, again, base times height. Well, what's the base of this rectangle? Well, it's going to be b minus what? x2. And what's the height of the rectangle? Still the same. 1 over b minus a. And that's the area, or excuse me, that's the formula for finding the probability of greater than or equal to. Okay? Now, what about between? What if we're interested in the area between these two? Well, same thing. We want the probability that x is less than x2 and greater than x1. Well, what's the base of this rectangle? It's just x2 minus x1, right? So it's just going to be x2 minus x1 times what? The height. What's the height? The same thing. 1 over b minus a. There you go. So that's it. So all you have to do is apply what we know about rectangles. And how do you calculate the area of a rectangle? Base times height. That's it. So there's no function on the calculator to give you these probabilities because quite honestly, it's just too easy to do. Okay? So you should have no trouble calculating probabilities and figuring out the average of a uniform distribution. The only thing really you have to remember is the formula for the variance. That's it. If you just remember the formula for variance for a uniform distribution, you can figure out everything else. Okay, especially standard deviation. The rest of this you can figure it out just by thinking about it. Okay, so let's do an example. So, let me see if I can do a good one here. Okay, what about, we'll do this one. It says, now we've got a data set, and so let me write out the data set. So it says, the data that follows are the number of passengers on 35 different charter fishing boats. The sample mean equals 7.9. Oops. The standard deviation is 4.33. The data follow a uniform distribution where all values between and including 0 and 14 are equally likely. So what does that mean? It means x is uniformly distributed what? from 0 to 14. There's your A and B. Why is it uniform? Because it says the number of passengers are equally likely. Okay, so the number of passengers for each of the charter ships, it's equally likely from 0 to 14. Okay, so the minimum number of passengers you could have is 0. The maximum number of passengers on any charter ship or charter boat is going to be 14. So it's uniform from 0 to 14. State the values of A and B. Well, we just did, 0 and 14. Write the distribution in the proper notation. Well, we just did. X, what is X? X is the number of passengers on a charter boat. What's the distribution? Uniform. What's A and B? 0 and 14. Now, it says calculate the theoretical mean and standard deviation. So we don't even need to look at the data for this, right? So in fact, we don't even need this. Okay? What is the theoretical mean? That's mu. Well, our formula is what? A plus B divided by 2. So it's going to be 0 plus 14 divided by 2, which is 7. So the average number of passengers per ship is 7. Now, look what we got from the sample mean. It was 7.9. So it's pretty close. And we're about a passenger off, but it's still pretty close. Okay? So now, what about the standard deviation? Well, the standard deviation is going to be what? B minus A divided by the square root of 12. Okay? So what is B minus A? 14. It's 14 minus 0 over the square root of 12. So what do we get? Well, let's find out. .04. Okay. So not bad. I mean, 7, 4.04, these are the theoretical values, and this is what we got from a random sample. So not bad, not bad. So let's see, what else? And of course the variance would be just that squared. Okay, what about this? What about a probability question? So now that we have this, okay, let's ask what's the probability that if we select a random charter, okay, what's the probability that the number of passengers on a randomly selected charter boat is going to have more than what? Let's say more than 8 passengers. Okay. Well, let's draw out our diagram and see if we can figure this out. So here's our diagram. Okay. So it starts at 0 and it goes to 14. So 0 to 14 passengers. So this is the number of passengers, right? This is X. And so now, well, here's our rectangle. Let's just draw it out this way. Okay, so here's our rectangle. Well, where's 8? Let's say 8 is somewhere over here. Okay, so we want greater than 8. So what's the area that we're interested in? It's going to be this area. Okay, so how do we figure out the probability? The area of the rectangle. So, remember it's base times height. Okay, so what's the base? The length of this side, right? So what is it? It's just 14 minus 8, right? The distance, right? So it's going to be 14 minus the 8 is going to be this length. So what is it going to be? It's going to be 6. Now, what's the height of this rectangle? Well, remember the formula for the height, right? What's the base of this whole rectangle, right? The base is 14. Well, what does the height have to be in order for this area to add up to 1? It has to be the reciprocal, 1 over 14. So this f of x has to equal 1 over 14. So that's the height of the rectangle. So this will always be, for this problem, 1 over 14. So now, what's the probability of being greater than 8? It's going to be 6 over 14, or 3/7. Which is going to be equal to point 0.429. Okay? And that's it. So let's do another one. What would the probability, let's say we want to know the number of passengers that represent the 85th percentile. So in this case here, we're giving a percentile. Well, what is a percentile? Remember from the definition of percentile from chapter 2 is it's the percentage of values or the percentage of data that falls at or below a given value. Well, in this case here, the given value x is a number of passengers. We don't know what that is. But we do know that whatever that number is, 85% of all of the data, or in this case, the number of passengers, falls below that value. Okay, so let's draw our diagram again and see what this looks like, right? So we know we have something that goes from 0 to 14. The height of this is 1 over 14. And we want to find the cutoff. So we're looking for a number of passengers. But what do we know? We know that this is at the 85th percentile. So we know that 85% fall at or below, which means the area under this curve is what? 0.85. So now we know what we're doing. We know that the area has to be equal to 0.85 for this x value. Well, we can find this x value if we apply the definition of a percentile and find the equivalent probability statement for this, right? So what does it mean to be the percentile? Well, I've already said it a couple times. Less than or equal to, right? So if we look at its area under the curve, then it's a probability. So we can connect the dots as far as a percentile with a probability now. So the probability is going to be that x is less than or equal to whatever value this is, right? X, we don't know. That's what we're trying to find. But we do know that this probability has to be equal to 0.85. Well, how do we calculate the probability of this? Well, remember our formula? Base times height. So what's the length of the base here? It's going to be what? X minus 0. So it's just x times the height. What's the height? 1 over 14 equals 0.85. Now we can solve for x, and we're done. So how do we solve for x? Multiply by the reciprocal on both sides. So I'm multiplying by 1/14. So to get rid of this, I have to multiply both sides by what? 14. So if I multiply both sides by 14, I get x equals 0.85 times 14. And what do I get? Well, just multiply. So 0.85 times 14, 11.9. So, in other words, approximately 12 passengers. So, if we have 12 passengers means that that represents the 85th percentile for all passengers. So if there's, if a charter has 12 passengers on the ship, it means that, hey, that number of passengers represents the 85th percentile, because if we look at all charter ships, 85% of all charter ships are going to have, or excuse me, 85% of all charter ships are going to have 12 passengers or less. That's what I mean to say. Okay? So that's how we can use percentiles and the uniform distribution to figure out what the x value is, or where the cutoff is for the particular percentile. Now, let's do one more with this case. Now, let's say we want to know what's the probability that a randomly selected charter is going to have more than more than 10 passengers if we already know that there's more than 3. So in other words, what's the probability that x is more than 10 given, right, so this is a conditional probability question, right? Given that we already know that x is more than 3. So now, in this case, what do we know? We know that there's already more than 3 passengers on the ship, or on the charter. So do we care about anything before that? No. We already know that there's more than 3 passengers. So what does that mean? We can ignore everything less than 3. Okay? What does it do to our distribution? Well, remember in chapter 3 when we talked about conditional probability that it changes our sample space. Well, here it's going to change our sample space as well. So what happens? Do we care about what happened before, three passengers? No, because we know there's more than 3. Okay, so now what happens to our A and B? Well, now our uniform distribution changes. No longer are we interested from 0 to 14, but now we are going to change to 3 to 14. So see how the given information changes our sample space. So now, to figure out this probability, we're now going to use this distribution. Okay? So now, what happens? What's our rectangle look like now? Oops. It's going to look like that. So now what happens to the height of a rectangle? Remember, the rectangle still has to, the area still has to equal 1. Well, what's the new base? Well, the new base here is 11 now, not 14. So what happens to the height of a rectangle? Well, f of x is now 1 over 11, not 1 over 14. So our height of a rectangle went up Why? Because the base of a rectangle shrunk, the sample space. Make sense? So now, this is what we have to use. Now, what's the probability that x is bigger than 10, given that we know x is bigger than 3? Well, now, this is what we're dealing with. So how do we do this? Now, we take base times height. What's the base? 14 minus 10, which is 4, times the height, which is now 1 over 11. And so we get 4 over 11, which is equal to what? 0.364. That's it. That's how easy it is. And so this is an example of using conditional probability with the uniform distribution. So that's going to be it for uniform distribution. So there are other examples. Again, if you're viewing this in my class, there are other examples in the textbook. There are other examples in the PowerPoints. Make sure you review those and understand how those work. And if you have any questions, reach out to me. Other than that, I hope you enjoyed this presentation, and I'll see you next time. Bye.